You are looking at the very edge of time, or at least what you think is the edge of time. Imagine staring into the darkest, emptiest void of the ancient cosmos, expecting to see absolutely nothing. But then, across a gap of over 13 billion years, a light blinks. It doesn't just shine, it flickers, like a candle burning in a room that hasn't been built yet. And that single, random flicker is hiding a terrifying secret about how the universe actually began. To understand what this flicker means, you have to let go of everything you think you know about time and space. We are not talking about a star in our local neighborhood. We are talking about a distance so unimaginably vast that the light we are seeing left its source just 850 million years after the Big Bang, a time astronomers call the cosmic dawn. To put that scale into perspective, if the entire 13.8 billion year history of the universe were compressed into a single human life, this light was emitted when the universe was just a toddler learning to walk. It should be an era of small, quiet, nascent things, simple gas clouds, tiny sputtering baby stars. But it isn't. This flicker belongs to something monstrous, something with the brilliance of 12 trillion suns, raging in the dark. It is a supermassive black hole, a voracious quasar, and the fact that it is flickering at all means it is eating. But what should keep you awake at night isn't how bright it is, or even how big it is. It's the structure hiding inside that flickering light. A structure that, according to the laws of physics, has absolutely no right to exist in the early universe. And the answer to how it got there is about to rewrite our entire cosmic origin story.
Let's step back and look at the anatomy of a void. When you walk outside on a clear, moonless night and look up, your brain tells you a very convincing lie. It tells you that the sky is a ceiling, a static, glittering dome painted with stars that exist right now, exactly as you see them. But that is an illusion born of our sheer insignificance. Space is not a place you are simply looking at. It is a four-dimensional landscape. And when you look up, you are not just looking across distance. You are looking backward through time. To understand the sheer, terrifying weight of what astronomers found hiding at the edge of the universe, you first have to understand the mechanism that keeps us trapped in the past: the speed of light. Light is the fastest thing in the cosmos. It travels at a blistering 186,000 miles every single second. To a human mind, that speed is almost incomprehensible. If you could travel at the speed of light, you could circle the Earth's equator 7.5 times in the time it takes you to blink. You could reach the moon in 1.3 seconds. You could arrive at Mars in just over 3 minutes. But out in the true deep of the cosmos, the speed of light is agonizingly, tragically slow. The universe is so unspeakably massive that light, the absolute speed limit of reality, crawls like a snail across the abyss. Because it takes time for light to cross these unfathomable distances, every single thing you see in the night sky is a ghost. You never see the universe as it is. You only see it as it was.
When telescopes like Hubble and the James Webb Space Telescope stare into this blackness, they capture light that has been traveling for billions of years. They are peeling back the layers of the universe's history, watching galaxies rewind. The further they look, the younger the universe gets. Eventually, if you look far enough, you hit a wall. You hit an era astronomers call the cosmic dawn. This is the epoch roughly 850 million years after the Big Bang. In the grand 13.8 billion year lifespan of the universe, 850 million years is nothing. If the entire history of the cosmos was a 24-hour day, the cosmic dawn happens in the first hour and a half. It is the dawn of creation, the nursery of the cosmos, the era when the very first stars were just igniting, burning away the thick primordial fog of hydrogen gas that choked the early universe. For decades, cosmologists told us a very specific, very comforting story about this era. It was a story of humble beginnings. The laws of physics dictate that massive, complex things do not just pop into existence. They have to be built. They require raw materials, gravity, and above all else, they require time. The standard model of the universe insists that the first black holes were relatively tiny. They were born from the collapsed cores of the very first stars, objects maybe 10 to 100 times the mass of our sun. By cosmic standards, these are absolute lightweights. For these tiny stellar mass black holes to grow into the supermassive leviathans we see today, the monsters with the mass of billions of suns that anchor modern galaxies, they have to eat. And eating takes time. They have to slowly, messily swallow surrounding gas, merging with other black holes in a process that takes billions upon billions of years to complete. It is a slow, methodical march from the simple to the complex.
That was the timeline. That was the rule book written into every astrophysics textbook on Earth. Growth requires time. But when the light from that 14-year flicker finally completed its 13-billion-year journey and fell onto the sensors of the Neowise telescope, it didn't just challenge that rule book. It tore it to shreds. Because if growth requires billions of years, and the universe at the cosmic dawn had only existed for a fraction of that, what exactly was casting such a colossal, flickering shadow in the dark? But science is rarely comforting, and the universe has a habit of leaving doors open where we thought the architecture of reality was completely locked down. To find this particular open door, we don't look to a giant multi-billion-dollar space telescope pointed at a single pixel for weeks on end. Instead, we look at an old, tireless workhorse, NASA's Wide Field Infrared Survey Explorer, or Neowise. For 14 long years, this satellite quietly orbited the Earth, mapping the entire sky in infrared light, over and over again. It wasn't looking for a specific mystery. It was just recording data. Millions of rows of raw, cold numbers, cataloging the background radiation of the cosmos. For over a decade, those numbers sat in digital archives, a silent testament to a sky that most people assumed was perfectly understood. Then, a team of astrophysicists at the Massachusetts Institute of Technology decided to look closer. They weren't looking at individual images. They were looking for movement. They were looking for change across time. They ran the 14 years of archival data through custom algorithms, looking for any pinpoint of light at the edge of the universe that wasn't behaving itself. And in the middle of that vast digital haystack, a single needle began to twitch. The algorithms flagged a specific coordinate in the deep sky. To the human eye, even through a powerful ground-based telescope, it looked like nothing more than a faint, microscopic speck of red dust. But the data from Neowise revealed that this speck was alive with activity. It wasn't a steady, reliable beacon. It was fluctuating. Over the course of those 14 years, its brightness didn't remain constant. It spiked and plunged wildly, dancing to a random, chaotic rhythm. When the researchers isolated the signal, they realized they were looking at a variance in light output that defied comprehension. This tiny speck wasn't just dimming and brightening by a few percentage points. It was changing its energy output by an amount equivalent to the total light of 2 trillion suns. Imagine turning a flashlight on and off, but every time you click the switch, the power of trillions of stars is either summoned or extinguished. And it was happening randomly, over spans of weeks, months, and years. To an astronomer,
This kind of erratic behavior is a universal fingerprint. It is a signature we recognize instantly because we see it in our modern local universe. It is the definitive profile of an active galactic nucleus, specifically a quasar.
We know exactly what causes a nearby quasar to flicker like this. In the center of mature galaxies, supermassive black holes sit surrounded by an incredibly dense, spinning whirlpool of gas, dust, and torn-apart stars. This is the accretion disk. Because a black hole cannot swallow an infinite amount of matter all at once, the material jams up at the event horizon, rubbing together at relativistic speeds. Friction heats this orbital ring of gas to hundreds of millions of degrees, causing it to glow with a fierce, blinding light that can outshine the entire galaxy hosting it. But a black hole is a messy eater. As it feeds, massive clumps of gas break off from the inner rim of the disk and plunge into the abyss. Magnetic fields twist, snap, and reconnect, unleashing titanic flares of energy. When a massive cloud of matter falls in, the disk flares bright. When there is a temporary lull in the supply line, the disk dims. The flickering is quite literally the sound of a cosmic monster chewing on its meal. It is a process driven by complexity, density, and immense gravitational maturity. In our modern neighborhood of space, seeing a quasar flicker over a 14-year period makes perfect sense. Those black holes have had 10 billion years or more to anchor themselves, gather materials, stabilize their orbits, and establish a steady, albeit messy, feeding routine. They are old, seasoned predators operating in a mature universe. But this newly discovered flickering signal wasn't coming from our neighborhood. When the MIT team analyzed the redshift of the light, measuring how much the expansion of space had stretched the light waves into the infrared spectrum, the results came back like a physical blow. The light wasn't from a nearby galaxy. It had been traveling for 13 billion years. This monster wasn't operating in a comfortable old universe. It was raging in the dark just 850 million years after the Big Bang. At a time when the universe should have been an empty, quiet nursery filled with nothing but cold gas and the very first fragile clusters of baby stars, this single object was sitting in the void, flashing with the power of trillions of suns. It was an impossible signal, shouting across time, forcing us to ask a question our current physics wasn't prepared to answer. But here's what the data didn't expect. When the MIT team calculated the energy required to create a flicker visible from 13 billion light years away, they realized they weren't looking at a growing baby black hole. They were looking at a fully formed monster, shining with the light of 12 trillion suns. It was already massive. The question was no longer if supermassive black holes existed at the dawn of time, but how something so unimaginably huge could form when the universe had barely even started.
Imagine walking through a prehistoric landscape. The earth is young, the air is thick with primitive gases, and the early ancestors of humanity have only just figured out how to shape a jagged rock into a basic hand axe. They are standing around a campfire, struggling to comprehend the concept of the wheel. And there, right in the middle of their camp, sits a towering, gleaming skyscraper made of titanium and glass, humming with electrical power. That is the exact scale of the paradox global astronomers were staring at. By finding a fully mature, hyperluminous quasar just 850 million years after the Big Bang, science had effectively stumbled upon an impossibility. The universe simply hadn't existed long enough to build something that big. It was a cosmic artifact out of time. But as the initial shock of the discovery began to fade, a new, more frustrating crisis took its place. It is one thing to look at a data set, point to a flickering line on a graph, and say, something massive is out there. It is another thing entirely to look that monster in the face. To truly understand how this skyscraper was built in the Stone Age of the cosmos, astronomers needed to see the blueprint. They needed to pull back the veil of light and inspect the geometry of the beast. Specifically, they needed to see its accretion disk, the ring of hyperheated matter swirling around the black hole's event horizon.
If they could see how that gas was moving, how it was structured, and how quickly it was falling into the void, they could finally deduce the secret of its impossible growth. But this is where humanity ran headfirst into a brutal, unforgiving technological wall.
To understand why we were trapped in the dark, you have to realize just how small the deep universe looks to us. The supermassive black hole at the center of this ancient quasar is undeniably massive, likely billions of times the mass of our sun. Its accretion disk is a yawning maelstrom of plasma that spans billions of miles across, a distance that could easily swallow our entire solar system whole, from the sun all the way out to Pluto and beyond. But across a distance of 13 billion light years, the laws of optics become a prison. When an object is that far away, its angular size in the night sky shrinks to almost absolute zero. To give you a human scale comparison, trying to resolve the shape of this accretion disk from Earth is mathematically identical to standing in New York City and trying to read the mint mark on a dime held up by an astronaut standing on the surface of the moon. It doesn't matter how advanced our technology is. It doesn't matter how pure the mirrors of our space telescopes are. Even the James Webb Space Telescope, with its massive beryllium gold primary mirror floating in the cold vacuum of space, hits a fundamental barrier dictated by the physics of light waves, the diffraction limit. When JWST peers at this impossible quasar, it cannot see a disk. It cannot see a structure. The light from that 12 trillion sun furnace is compressed, distorted, and squeezed by the sheer expanse of space until it strikes the telescope's sensors as a single, solitary pixel of data. One pixel. Inside that single flat dot of infrared light, the entire epic story of the early universe was blurred together. The black hole, the spinning plasma, the screaming magnetic fields, the birth of the surrounding galaxy, all of it was locked inside a single point of light that could not be magnified, split, or resolved by any lens humanity could ever construct. We were standing on the edge of the ultimate truth, completely and utterly blind. Or so we thought.
For months, the mystery remained a dead end. Theoretical models were flying back and forth, but they were nothing more than educated guesswork. Some scientists argued the black hole must have formed from the direct collapse of a massive primordial gas cloud, bypassing the star phase entirely. Others claimed it must have been feeding at a hyper-Eddington rate, stuffed with matter far beyond the standard theoretical limits of physics. But without a visual map of the accretion disk, there was no way to prove who was right. The single pixel refused to give up its secrets. Space had won. It had kept the shadow of the beast hidden behind a wall of distance too vast for human lenses to pierce. But human curiosity is a dangerous thing. When you block an astronomer's path in space, they will find a way to circumvent it using a completely different dimension. The team at MIT realized that while they couldn't expand the pixel across a physical lens, they could watch how that pixel changed across the linear progression of time. If space wouldn't give them a map, they would force time to draw one for them. Repug, triggered by using time to map space. But here's what researchers realized they could do. They couldn't use a physical glass lens to see the black hole, but they could use time as a chronological microscope. By tracking exactly how the light within that single pixel flickered over a grueling 14-year period, they realized the delays in the light waves acted exactly like an interstellar sonar ping. The flicker wasn't just random, meaningless static noise, it was a highly precise mathematical echo chamber. The flashes of light from the inner rim of the black hole were bouncing off the outer edges of the gas cloud, leaving a time-stamped signature of the invisible structure. And when they finally decoded that temporal map, the geometry they found broke our understanding of cosmic dawn entirely. But here's what researchers realized they could do. They couldn't use a lens to see the black hole, but they could use time. By tracking exactly how the light flickered over 14 years, the delays in the light waves acted like a sonar ping. The flicker wasn't just random noise. It was a mathematical map of the invisible gas swirling around the abyss. And when they decoded that map, the shape they found broke everything. If you were to sit down with a theoretical physicist and ask them to draw a blueprint of what a young, early universe black hole should look like, They wouldn't draw a neat, elegant ring. They would draw a picture of absolute, unadulterated chaos. Think about the sheer physics of the situation. To build a black hole containing the mass of 1 billion suns in less than 850 million years, you cannot afford to be elegant. You cannot afford to be patient. You have to force-feed the gravity well at a rate that pushes the absolute boundaries of fluid dynamics and relativity. Because of that frantic, desperate rush against time, the standard cosmological models are very clear about what the environment around the abyss must look like. The gas falling into a baby supermassive black hole shouldn't have time to organize itself. It should be a violent, multi-directional stampede. Astronomy calls this a chaotic spherical accretion envelope.
Imagine a massive, turbulent swarm of hyperheated plasma attacking the event horizon from every single direction at once. Gas screaming in from the North Pole, dust crashing in from the south, stellar remnants colliding at relativistic speeds along the equator. It is a three-dimensional cloud of hyperdense, glowing friction. Because the material is choking the black hole, the magnetic fields are constantly twisting into knots, snapping like cosmic whips, and blasting violent jets of radiation randomly out into the primordial void. It should look like an unruly, blindingly bright storm, a disorganized sphere of fire. That chaotic, spherical structure is more than just a visual. It is the definitive signature of youth. It is the anatomical proof of a black hole caught in the middle of a frantic, messy, hyper-accelerated growth spurt. When the MIT team finally finished processing their 14 years of temporal data, this is exactly what they expected to see mapped out by the light echoes. The mathematics of the flickering should have traced the rough, uneven contours of a turbulent sphere. It was the only logical way to explain how a monster of that scale could exist so early in time. It had to be violently gorging itself on a chaotic, three-dimensional supply line. The researchers ran the numbers through their supercomputers, waiting for the simulation to spit out the coordinates of a chaotic spherical storm. They waited for the data to confirm our long-standing theories of early universe chaos. But as the millions of data points settled into a visual model, the shape that materialized on their screens didn't look like a storm at all. The points didn't form a sphere. They didn't outline a chaotic, turbulent swarm of multidirectional gas. Instead, the time-delayed echoes of light traced a structure that was shockingly, impossibly organized. It was a single, clean, razor-thin plane. A perfectly flat, beautifully aligned pancake of rotating plasma, spinning with the serene precision of a grandfather clock.
But here's what the observations completely proved wrong. The map didn't show a chaotic, fast-growing baby sphere. It showed an incredibly stable, fully mature accretion disk, a structure that under normal conditions takes billions of years of slow gravitational friction, angular momentum dissipation, and calm orbital evolution to settle into. Yet the universe around it was only 850 million years old. We weren't looking at a monster in the middle of a violent, messy growth spurt. We were looking at a pristine, ancient, perfectly stabilized structure sitting in a universe that had just opened its eyes. The chaotic growth phase hadn't just happened faster than we thought, it was already completely over.
Imagine walking across a landscape of freshly hardened black lava, still radiating the immense heat of a recent volcanic eruption. The rock beneath your feet is jagged, sharp, and violently formed. But as you walk, you look down and see a perfectly smooth, beautifully rounded riverstone resting on the ash. Your brain instantly recognizes a contradiction. That smooth stone could only be created by thousands of years of rushing water, patiently grinding away its rough edges. But the island you are standing on was only born yesterday. This is the exact sensation astronomers felt when the temporal map of this ancient quasar finally rendered on their screens. A perfectly flat, razor-thin accretion disk is the cosmic equivalent of that smooth riverstone.
It is an object that explicitly requires a massive amount of time to form, sitting in a universe that hasn't had the time to make it. To understand why a flat disk is the ultimate smoking gun of cosmic age, we have to look closely at the invisible, unforgiving mechanics of gravity and motion.
In the vast, frictionless vacuum of space, chaotic things do not naturally calm down. If you have a massive, turbulent sphere of gas falling into a black hole from all directions, it doesn't just neatly organize itself because gravity tells it to. For a chaotic sphere to flatten out into a pristine disk, it has to obey the law of conservation of angular momentum. You've seen this law in action on Earth. Think of a chef tossing a rough, spherical ball of dough into the air and spinning it. As it spins, the outward centrifugal force causes the dough to flatten out into a wide, thin disk. The exact same physics govern the largest structures in the universe, from the rings of Saturn to the spiral arms of the Milky Way galaxy. But there is a massive difference between pizza dough and a cloud of hyperheated plasma spanning billions of miles. For a cosmic gas cloud to flatten, it requires something incredibly rare in the emptiness of space: friction. As the turbulent gas falls toward the event horizon, particles traveling in opposite directions must physically crash into each other. Gas clouds moving north to south have to collide with clouds moving south to north. These titanic, microscopic collisions cancel out their vertical momentum, leaving only the horizontal spin. Slowly, agonizingly, the violent three-dimensional storm grinds itself down into a two-dimensional plane. But friction on a cosmic scale is not instantaneous. It is a grueling, unimaginably slow process of attrition. Astrophysicists can calculate exactly how long this settling process should take. For a supermassive black hole with the mass of 1 billion suns to grind its chaotic feeding sphere down into a razor-thin, stable accretion disk, the gas must orbit the black hole millions, if not billions of times. In our modern universe, this is not a problem. Black holes have had nearly 14 billion years to let their meals settle. But let's look at the timeline of the cosmic dawn. The universe was roughly 850 million years old when the light from this flickering quasar began its journey to Earth. But the black hole didn't form at the exact moment of the Big Bang. First, the universe had to cool down. Then, the first atoms had to form. Then, those atoms had to clump together over millions of years to form the very first massive stars. Finally, those stars had to burn through their fuel and collapse into the first stellar mass black holes. By the time the very first baby black holes were actually born, the universe was already several 100 million years old. That left this particular monster with only a few 100 million years to not only grow to the size of 1 billion suns, but also completely stabilize its massive accretion disk. Mathematically, physically, and logically, there simply wasn't enough time.
When the MIT data was published, it sent a shockwave through the theoretical physics community. Models were immediately torn apart and rewritten. In a desperate attempt to explain how a black hole could get this big and this mature this fast, scientists turned to an exotic, highly controversial theory: heavy seeds. The standard model says black holes start as light seeds, the dead cores of single stars. But to solve this timeline crisis, theoreticians proposed that perhaps in the thick primordial soup of the early universe, monstrous clouds of gas containing the mass of 100,000 suns completely bypassed the star phase. Instead of igniting into stars, these colossal clouds collapsed directly under their own staggering weight, instantly punching a massive hole in space-time. They were born big, heavy seeds. If this quasar was born from a heavy seed, it wouldn't have needed billions of years to grow from a tiny stellar remnant. It would have started its life already massive, aggressively swallowing its surroundings. But even this exotic, rule-breaking theory fails to explain the flat disk. Even if a massive gas cloud collapsed directly into a giant black hole, the environment around it would still be chaotic. The sudden, violent collapse of 100,000 suns worth of gas would create an unprecedented gravitational tsunami. The feeding process that followed would be exactly what we expected:
a disorganized, multi-directional spherical storm of fire. A heavy seed explains the mass. It does absolutely nothing to explain the maturity. And so, astronomers are left staring at an artifact that refuses to fit into the timeline of reality. We are looking at a structure that vividly remembers billions of years of history in a universe that hasn't lived them yet. It forces us to look into the absolute darkness before the cosmic dawn and ask a terrifying question. Are we miscalculating how fast black holes can evolve? Or are we missing massive, fundamental pages from the very beginning of the book of time itself?
When every single theoretical model of visible matter fails to explain reality, scientists are forced to do something deeply uncomfortable. They have to stop looking at the light, and they have to start looking at the dark. If normal gas dynamics, if the laws of cosmic friction, and if even the exotic theory of direct collapse heavy seeds cannot explain how a perfectly flat, elegantly mature accretion disk existed just 850 million years after the Big Bang, then we must accept a terrifying truth. The answer cannot be made of normal gas. The physics of regular matter, the glowing, interacting, colliding stuff that makes up you, me, the Earth, the stars, and the fiery rings of black holes, has reached its absolute limit. It has failed to explain the artifact we are staring at. To solve the paradox of this ancient, flickering quasar, astronomers had to ask a question that borders on the supernatural. They had to ask if there was an invisible hand at work, an unseen silent architect that guided the rapid, seemingly impossible maturation of this cosmic leviathan, bypassing the need for billions of years of friction entirely. And in the universe, the ultimate invisible architect is dark matter. We humans have a very biased view of reality. Because we have eyes that evolved to detect photons, we naturally talk about the universe as a collection of glowing things. Stars, galaxies, shimmering nebulas, and blazing quasars. But that glowing matter, everything we can see, touch, interact with, and measure with our standard instruments, makes up a pitiful 5% of the cosmos. It is nothing but a dusting of snow on the tip of a massive unseen iceberg. The vast majority of the mass in the universe is tied up in dark matter. We don't know what it is. We can't see it, we can't taste it, and it completely, fundamentally ignores light. A beam of light will pass straight through a wall of dark matter as if nothing is there. But it exerts a terrifying, undeniable amount of gravity. In our modern, local universe, dark matter acts as the cosmic glue. It is the invisible web holding galaxies together. Without its immense, unseen gravitational grip, the spinning spiral arms of the Milky Way would literally fly apart, scattering our sun and billions of other stars out into the freezing, empty void. But in the early universe, during the chaotic epoch of the cosmic dawn, dark matter wasn't just holding things together, it was actively building them.
To understand how dark matter built an impossible black hole, you have to look at the timeline of the Big Bang. In the immediate aftermath of the universe's birth, everything was unimaginably hot. The normal, visible matter was a blindingly bright, hyperheated fog of plasma. It was so hot and vibrating with so much kinetic energy that it simply couldn't clump together. If gravity tried to pull two clouds of normal hydrogen gas together, the sheer heat and pressure of the radiation would violently blast them apart again. Visible matter was trapped. It had to wait. It had to wait hundreds of millions of years for the universe to expand and cool down enough before it could safely begin to gather, condense, and form the first stars. But dark matter doesn't care about heat. It doesn't interact with radiation. It is entirely immune to the blinding flashbang of the early cosmos. Because of this chilling immunity, dark matter didn't have to wait for the universe to cool down. Millions of years before the first star even thought about igniting, while normal matter was still a chaotic, blinding fog, dark matter was already hard at work in the shadows.
It was already clumping together, collapsing under its own weight, and building the foundational architecture of the universe.
These massive, invisible structures are called dark matter halos. But the word halo sounds too delicate. Think of them instead as colossal, invisible gravity craters, unfathomably deep, unseen wells sinking into the fabric of space-time itself. By the time the visible universe finally cooled down enough to allow normal hydrogen gas to clump together, the dark universe was already highly evolved. The invisible craters were already there, waiting. And when the gas finally stopped violently bouncing off itself, it didn't just drift aimlessly through an empty void. It was violently, unstoppably pulled down into the centers of these massive, pre-existing dark matter sinkholes. For a long time, astrophysicists thought these dark matter halos were just giant static bowls holding the cosmic soup. They thought the gas just fell in, gathered at the bottom, and began the slow billion-year process of chaotic friction to form black holes and disks. But the discovery of our impossible flat-disked quasar forced researchers to run entirely new, hyper-advanced supercomputer simulations of the cosmic dawn. They had to see what would happen if those early dark matter halos weren't just sitting still. What if they were moving? What if, in the total darkness of the infant universe, they were spinning? In the frictionless vacuum of space, things rarely sit perfectly still. As these massive, invisible clumps of dark matter merged together in the early universe, their combined momentum caused them to rotate. And because they contained the mass of trillions of suns, their rotation created something monstrous. It created a gravitational vortex. Imagine you are standing on the deck of a ship in the middle of a pitch-black ocean. The water itself is entirely invisible to you. You cannot see the waves, you cannot see the currents, and you cannot see the churning depths. But suddenly, your ship is caught up in a massive, miles-wide whirlpool. Even though you can't see the water, your ship doesn't just float randomly. It doesn't slowly bump into other debris until it finds a path. It is violently, instantly forced to follow the exact, swirling, flattened shape of the vortex beneath it. The invisible current dictates everything. This is the terrifying, beautiful answer the MIT supercomputers finally spat out. The perfectly flat, mature accretion disk of this ancient supermassive black hole wasn't created by billions of years of normal gas grinding against itself. It didn't need time. It didn't need friction. It was forced into that shape by an invisible mold. When the normal glowing hydrogen gas of the early universe was pulled down into this specific dark matter halo, it was falling into a colossal, rapidly spinning dark tornado. The invisible scaffolding of the universe was already perfectly flat, already rotating with immense, mature power, hundreds of millions of years before the gas even arrived. When the matter fell into this dark vortex to feed the growing black hole, it had absolutely no choice. It didn't have to spend a billion years slowly canceling out its vertical momentum. It was instantly grabbed by the gravitational shear of the dark matter tornado and snapped into a razor-thin disk, obeying the iron grip of the phantom mass around it. The chaos was bypassed entirely. The timeline wasn't broken. It was just being driven by an engine we couldn't see. This single realization fundamentally, permanently shifts our place in the cosmic hierarchy. We have spent centuries looking through our optical telescopes, studying the brilliant light of quasars, charting the majestic sweeping arms of spiral galaxies, and mapping the glowing nebula. We thought that visible matter was the main character of the universe. We thought the supermassive black holes were the ultimate architects, slowly shaping the cosmos around them through their chaotic, ravenous feeding over eons of time. But this 14-year flicker from the edge of time tells a much darker, much more humbling story. The glowing monsters didn't build the house. The house was already built, entirely in the dark, long before the lights were ever turned on. The supermassive black holes at the cosmic dawn, with their perfectly flat, mature accretion disks, were just filling in the empty spaces of a ghost structure that predates the visible universe itself. The visible universe isn't a slow, evolving entity carving its own path through the void. It is nothing more than glowing paint,
helplessly pored over the ancient, invisible machinery of a dark universe. A dark universe that was born mature, born spinning, and born waiting for the light to finally arrive.
Imagine waking up one morning, walking out of your front door, and realizing that the city you have lived in your entire life, the streets you walk, the buildings you work in, the bridges you cross, were not built by human hands. Imagine discovering that humanity simply moved into a sprawling, hyper-advanced metropolis that was already constructed, entirely in the dark, by an invisible civilization long before we arrived. That is the existential shock currently echoing through the halls of modern astrophysics. By accepting that a dark matter tornado physically forced an impossible flat accretion disk into existence just 850 million years after the Big Bang, we are crossing a psychological Rubicon. We have to fundamentally accept that visible matter, the protons, neutrons, and electrons that make up our bodies, our planets, and our suns, is not in charge. We are not the architects of reality. We are simply passengers, riding on a train whose tracks were laid out in the absolute pitch-black darkness of the primordial universe. This realization changes the entire premise of the cosmic dawn. For decades, when we looked at the infant universe, we thought we were looking at a quiet, empty void where things were slowly, painstakingly trying to organize themselves. We pictured isolated clouds of hydrogen gas randomly bumping into each other, struggling against the expansion of space to form the very first fragile stars. We thought gravity was a weak, slow-acting force that took billions of years to sculpt the galaxy. But this 14-year flickering signal from the void has exposed that entire narrative as a physical illusion. The early universe wasn't a disorganized nursery. It was a highly structured, violently active construction site. And the dark matter halos, these colossal, spinning, invisible gravity craters, weren't just isolated anomalies. They were everywhere. They were the foundational nodes of something infinitely larger, something so unimaginably vast that it forces us to rethink the very definition of a structure.
Astronomers call it the cosmic web. If you could step outside of the universe and look at it in its entirety, bypassing the blinding light of the stars and focusing only on the gravity, you wouldn't see a random scattering of galaxies. You would see a sprawling, interconnected, biological-looking nervous system. Trillions of miles of invisible dark matter filaments crisscross the void like glowing threads of spider silk. And wherever these massive, invisible threads intersect, they create a super dense gravity knot, a dark matter halo. What the James Webb Space Telescope and the MIT algorithms have begun to reveal is that these invisible intersections were already perfectly formed, fully mature, and spinning rapidly in the darkest era of time. They were massive, invisible funnels, waiting for the visible universe to catch up. When the normal hydrogen gas finally cooled down, it didn't just drift. It was violently dragged along these invisible highways, rushing at terrifying speeds toward the intersections. The gas was physically pouring into these spinning dark matter funnels like water violently draining down a cosmic sink.
This is why the black holes at the edge of the universe grew so impossibly fast. They weren't hunting for food. They didn't have to wait for stars to form, die, and merge. They were sitting at the exact center of a rigged system. The dark matter web was actively force-feeding them. Millions of suns worth of raw, primordial gas were being aggressively funneled down these invisible tornadoes, instantly flattened into razor-thin accretion disks by the sheer rotational force of the dark matter mold and shoved straight into the event horizon. The universe was literally engineered to build monsters. The visible gas had no choice but to form supermassive black holes almost instantaneously because the invisible architecture of the cosmos demanded it.
The dark matter was rushing the universe into maturity, bypassing billions of years of chaotic evolution and stamping out supermassive leviathans like a cosmic assembly line operating in the dark. But nature, even on a scale this terrifying, demands balance. If the entire invisible architecture of the early universe was designed to violently funnel limitless amounts of gas into these black holes, why didn't they just keep growing? If the dark matter tornadoes were so incredibly efficient at force-feeding the abyss, why didn't these monsters eventually consume the very galaxies they were anchoring? Why isn't the modern universe just a collection of impossibly massive, bloated black holes sitting in empty space? This is where the story of our perfectly flat, 13-billion-year-old quasar takes its final, most brilliant twist. The dark matter mold may have built the monster, but it didn't account for what happens when a monster wakes up.
When a supermassive black hole is fed that efficiently, and its accretion disk is squeezed into that perfectly flat, high-friction shape, it doesn't just quietly swallow the gas. It fights back. The sheer amount of material being forced into the flat disk causes the magnetic fields to warp and snap with unimaginable violence. The friction heats the plasma to hundreds of millions of degrees, and suddenly, the black hole does something the dark matter cannot control. It ignites into a quasar. It unleashes a torrent of radiation so blindingly intense, so unspeakably powerful that it outshines trillions of stars combined. But this light isn't just a visual spectacle. It has physical mass. It has physical force. Astronomers call it quasar feedback. The radiation blasting out from that perfectly flat disk hits the incoming hydrogen gas with the force of a cosmic hurricane. It creates a physical shockwave that slams into the gas pouring down the dark matter funnel, violently arresting its momentum. It is a battle of titanic, universal forces taking place at the very dawn of time. The invisible dark matter is trying to crush the galaxy down, aggressively feeding the black hole to make it infinitely larger. But the black hole itself, powered by the incredible efficiency of that flat disk, acts as a cosmic thermostat. The faster it is fed, the brighter it burns, and the harder it pushes the gas away. It stops its own growth. It stops the dark matter from collapsing the galaxy. It physically blows the remaining gas outward, cooling it down and giving it the exact, stable environment it needs to finally start forming normal, beautiful stars. The flat disk we saw in the data wasn't just an artifact of impossible age. It was the engine of creation. The invisible ghost built the monster, but the monster regulated the universe. They were locked in a perfect, highly calibrated, self-sustaining mechanical dance, operating with flawless precision before the universe was even a billion years old. It completely destroys the idea that we live in a random, chaotic cosmos. From the very first, darkest moments of existence, the universe wasn't stumbling in the dark. It knew exactly what it was doing.
In the world of paleontology, there is a terrifying, unspoken rule about the fossil record. If you were digging in a layer of rock that is 500 million years old, in an era where life on Earth was strictly supposed to be nothing but microscopic bacteria, algae, and soft, drifting jellyfish, and your shovel suddenly strikes the fully fossilized, massive skull of an apex predator, you don't just have a mystery on your hands. You have a catastrophe. Because a predator of that immense size and complexity does not exist in isolation. It cannot exist in a vacuum. A monster requires an ecosystem. It requires a food chain. It requires a breeding population. If there is one fully mature predator walking around in an era where it absolutely should not belong, it means you must accept the horrifying reality that millions of these creatures were hunting just outside your field of view. It means your entire map of history is not just slightly incorrect, it is completely, fundamentally broken. This is exactly where modern astrophysics finds itself today. We have found the impossible skull in the primordial rock. The single impossibly mature quasar at the edge of the cosmic dawn, with its perfectly flat accretion
accretion disk acting as a flawless cosmic thermostat is not a freak accident. It is not a bizarre statistical anomaly that we can just brush under the rug of standard physics. It is simply the first one that was loud enough and bright enough for our telescopes to hear.
Think back to the sprawling, invisible architecture of the dark matter web. That massive, interconnected nervous system of glowing threads and spinning gravitational tornadoes did not just exist in one single coordinate of the deep sky. It covered the entirety of the early universe. The dark matter web was everywhere. It was the underlying invisible fabric of the cosmos itself, which means the intersections were everywhere. If the physics of the invisible mold forced normal gas to instantly flatten into a mature accretion disk in this one specific location, it was doing the exact same thing across millions, perhaps billions of other invisible intersections at the exact same time. The universe wasn't just handcrafting one supermassive black hole in the dark. It was mass-producing them on an industrial scale. We are not looking at a lone anomaly. We are staring at the first confirmed outpost of an invisible empire. It is an empire of supermassive leviathans that were already fully grown, fully stabilized, and fiercely regulating the gas of the cosmos before the universe had even reached its first billionth birthday. The monsters were ubiquitous. They were the rulers of the dawn. And for the last 50 years of modern astronomy, because we were only looking for slow, simple, glowing things, we have been completely, humiliatingly blind to them. This terrifying realization is exactly why the James Webb Space Telescope has entirely pivoted its deep space focus. When JWST was first launched, scientists thought they were going to use it to gently peer into an era called the Cosmic Dark Ages. This was supposed to be a calm, quiet epoch, a span of hundreds of millions of years where the universe was draped in a pitch-black fog of hydrogen, waiting patiently for the very first tiny stars to slowly flicker to life. We thought we were going to watch a gentle, quiet sunrise. But armed with the mathematical signature of this ancient quasar, JWST is no longer looking for gentle baby stars. It is actively hunting the invisible dark matter tornadoes. And when astronomers point JWST into the absolute deepest, emptiest patches of the night sky, what they are finding is sending shockwaves of absolute panic through the theoretical physics community. The early universe is dangerously, impossibly crowded. Astronomers are now finding what they nervously refer to as little red dots. In the deep infrared images captured by JWST, these tiny red specks are everywhere. But they aren't stars. They are supermassive black holes, hundreds of them, thousands of them. Every time JWST stares deep into the ancient dark, it isn't finding a quiet cosmic nursery. It is finding blindingly bright, hypermassive galaxies that are already fully assembled. It is finding supermassive black holes anchoring star systems that shouldn't exist for another 5 billion years. The data is piling up so fast and is so violently opposed to the standard model of the universe that theoreticians are literally running out of ways to tweak the math to make it fit. We are trying to pour an ocean of impossible, hyper-mature galaxies into a teacup of outdated physics. It is breaking the minds of the people who thought they had the universe figured out. The truth that is slowly, agonizingly dawning on humanity is that there never were any cosmic dark ages. The universe did not wake up slowly. It was violently, aggressively thrown into maturity by the dark matter web. The engines of creation were redlining from the very first fraction of a second. But here is the thought that should truly keep you awake when you look up at the night sky tonight. In the previous chapter, we talked about quasar feedback, how the intense radiation from that perfectly flat disk blasted the incoming gas away, acting as a cosmic thermostat. It stopped the dark matter from crushing the galaxy, cooled the gas down, and gave it the exact, stable environment needed to finally form normal, beautiful stars. If you trace that invisible line of physics all the way through the history of time, it leads directly to you. Our own Milky Way galaxy has a supermassive black hole sitting in absolute silence at its center, right now. And surrounding our entire galaxy is a massive, invisible halo of dark matter. The very atoms of carbon in your muscles, the iron pumping through your blood, the oxygen filling your lungs right this second, all of it was forged in the hearts of stars that were only allowed to form because an ancient, supermassive black hole pushed the chaotic gas of the early universe into a perfect, stable balance. We used to look at black holes as the ultimate destroyers. We thought of them as cosmic grim reapers, lurking in the dark, waiting for the universe to age so they could devour the decaying remains of dead stars. But the 14-year flicker from the edge of time has permanently inverted reality. They are not the destroyers at the end of the line. They were the architects at the beginning. We are not the main characters of the cosmos, bravely evolving against the odds. We are the byproduct of their exhaust. The very existence of stable, life-giving galaxies like our own was dictated by the invisible tornadoes and the flat-disked monsters they birthed in the dark. We are the descendants of an impossibly violent, flawlessly engineered feedback loop. And if the universe was born this organized, this mature, and this perfectly calibrated, it leaves us standing on the precipice of a question that physics alone may not be able to answer. If the visible universe is just a helpless reaction to the dark, what exactly is the dark?
We have spent centuries looking through telescopes, telling ourselves a very comforting story about our origins. We wanted a story of humble beginnings, a chaotic Big Bang, followed by a long, dark, peaceful slumber. We wanted to believe that over billions of years, gravity slowly, gently, and randomly pulled the universe together, evolving step by step from the incredibly simple to the beautifully complex. We wanted to believe we were the apex of that long, slow climb. But this single 14-year flicker from the edge of time has burned that comforting story to the ground. The flat, impossibly mature accretion disk of this ancient quasar tells us a terrifying truth. The messy, chaotic, hyper-violent growth phase of the cosmos, the era where the monsters were truly made, didn't happen over billions of years. It happened almost instantaneously. In the darkest, earliest fraction of time, before the first starlight even pierced the void, the invisible scaffolding of the universe was already fully built. The dark matter tornadoes were already spinning. The gravity wells were already dug. The universe wasn't born simple. It was born terrifyingly complex. It was born monstrous. We missed the era of creation entirely. When we look at the cosmic dawn, we're not looking at the fragile seeds of galaxies. We are looking at the fully grown apex predators of the cosmos, already sitting on their invisible thrones, calmly feeding in the dark. Our entire model of cosmic evolution isn't just slightly off. It is radically, fundamentally upside down. The dark didn't just hold the universe together. It built the machines that made us, and it did it before the lights even turned on.
When you look up at the night sky tonight, you aren't just looking at stars. You are looking through a tapestry of invisible, ancient ghosts. There are monsters hiding at the very edge of our vision, quietly flickering in the dark, defying everything we thought we understood about the beginning of time. And if supermassive black holes could form and mature in the blink of a cosmic eye, it leaves us with an unsettling question. What else was hiding in the dark before the universe even turned the lights on? What do you think happened in those first unseen moments of the cosmos? Did gravity work differently? Let me know your theories down in the comments. I read every single one of them.
The universe is vast, and we have only just begun to open our eyes. Keep looking up.